Hi, my name is Manuel Almeida, and I'll be presenting our work, Smart at What Cost? Characterizing mobile deep neural networks in the wild. Deep neural networks have achieved wide adoptance, from smart virtual assistants all the way to self-driving cars. These models are no longer restricted to big data centers and are being more and more deployed into resource-constrained devices like mobile phones. While these model accuracies have been increasing, they often do so at an increased number of parameters, energy consumption, memory, and compute. And this is particularly problematic for resource-constrained devices like mobile phones, where inference takes orders of magnitude longer than executing on a desktop. Furthermore, there have been many developments on SOCs, like neural processing units, that have been included on mobile, and other technologies like ARM, Big Little, and Dynamic IQ that make the cores in the CPU heterogeneous in terms of frequency and energy with different trade-offs, okay? Nonetheless, with great flexibility also come great challenges. So for example, when deploying your neural network, you might target different frameworks with very distinct kernel optimizations. Different manufacturers might also have very different drivers and hardware accelerators. And distinct hardware architectures might actually have very different resources as well. All of these make it increasingly harder to predict and optimize the performance for each device tier. That's why in this paper, we set out to measure what the actual mobile machine learning landscape looks like in the wild by studying real-world DNNs as deployed with the most popular applications. To do so, we crawl, extract, and validate models at scale from the Google Play Store. We download dozens of thousands of applications. We perform static code analysis and native library inspection of them. We extract all the files from these applications and validate them to find deep neural networks, more details in the paper. And we use their official interpreters from the frameworks to get things like flops, parameters, layers, and shapes. And furthermore, we execute these models on device in order to get metrics like runtime resources, latency, energy, frequency, and so on. Here on the left, we show that our system is actually able to automate the full process of executing on device and also collecting all these metrics and cleaning up after itself. On the right side, we show the experimental setup. We have three different mobile devices of different tiers, low, mid, and high tier. And we also have three different tiers of hardware development kits from Qualcomm that are connected directly to a Moonsun powered monitor to get accurate energy measurements. So our very first research question is, given the forefront of machine learning research and the multitude of tools and devices in the wild, what kind of models are being deployed in mobile apps and utilized by developers and for which tasks? To answer this question, we condensed a data set of the 500 top applications per category of the Google Play Store. We are very surprised to announce that we were able to extract 90% of the models from the apps with models, details on the paper. We found no evidence of models being specialized for specific hardware SOCs. And most of the models out there are actually based on TF flight. In terms of snapshots, we actually took 2 snapshots of the applications, each snapshot with over 16,000 applications. And the most interesting thing about these 2 snapshots is that they are 1 year apart and they actually encapsulate the period of lockdown in COVID, okay? And the most interesting thing here is that we found that photography, which used to be the top category, actually got replaced by communications. And we also saw an uptrend of medical apps and a downtrend of lifestyle, foods, drinks, and wearables. And this might reflect the fact that people were actually staying indoors, okay? We saw also a 2x increase in the number of TF-like models, for example, and a 2x increase of the number of unique models across these last years. In terms of tasks, we find that vision is the most popular task. We also found that the heaviest task for vision is classification, error reconstruction, segmentation, beauty, while for NLP and audio, it's auto-completion and sound recognition, respectively. We also looked at model uniqueness, and we were very surprised to find that only 19% of the models are actually unique, MobileNet being prevalent across many of the tasks. In terms of individual layers, we were also very surprised to find that from the unique models, close to half of them actually only differ by 3 layers. And what does this mean? This means that basically it is common for developers to leverage a pre-trained model that is found off the shelf, like a widely available one, and to train it offline by training only a subset of the DNA, or some layers, okay? So we found evidence of fine-tuning. Nonetheless, we did not find any evidence of this actually occurring on device, okay? So our second research question is, in a highly heterogeneous ecosystem of smartphones, how are these models deployed and are they able to perform efficiently across different targets and tasks? Here we started by looking at latency. And while we found a lot of differences between different device tiers, the main takeaway here is that most of the models are quite lightweight compared to the state of the art, okay? We also looked at the tail of high latency models, and we see that it comes from some of the most flop intensive tasks. Nonetheless, we show in the paper that flops are not a perfect predictor for latency. In terms of energy, we see that a similar amount of energy is required for the same workload across devices. Nonetheless, the power consumption is actually quite different, with newer devices drawing way more power, but also executing much faster. In terms of flops per second per watt, we actually see that they are quite similar, but newer devices are slightly more efficient. And what is the main takeaway in this case? The main takeaway is that unlike latency, which is visibly improved with new versions of devices, energy consumption seems to be predominantly dependent on the model architecture. What this suggests is that it is the AI developers who can optimize battery life the most, unlike plain latency, which can be improved at multiple levels, including manufacturers, for example. We also designed a set of use cases by picking some of the models that we found in the wild, and we designed very realistic use cases around their tasks, okay? I'm not going to go into many details, but the main takeaway here is that if you grab a model for semantic segmentation, for example, with a very normal use case of just 1 hour call at 15 FPS, if this model is badly designed or badly optimized, it can actually almost completely deplete your battery. So the main takeaway here is that energy is becoming a bottleneck, and we as researchers need to find solutions to support mobile intelligence on the go. So the final research question is, what are the common model and system level optimizations being used to make inference in the wild faster on smartphones? And here we looked at model, system, and hardware level, actually. We found no evidence of clustering or pruning. While quantization is widely available, we only found that only 20% of the models actually use it for model compression, while only 10% of them use them to quantize activations. We also play in the paper with the scalability to increasing the batch size. And we also look at process spinning and find out that it is actually quite difficult to find a common setup that works well across device tiers. In fact, there is none. In terms of hardware-specific optimizations, we detail in the paper how there are many ways to execute your neural networks into the mobile hardware. And the main takeaway here is that while the de facto standard of Android, the Android NNN API, kind of abstracts a bit the complexity of the ecosystem, it is actually extremely slow and energy inefficient compared to targeting directly the CPU. Furthermore, there are other runtimes that could greatly speed up by up to 20x and make it way more energy efficient by up to 8x, but that they are not being widely adopted by mobile applications. And we believe this is because developers prefer generality over hardware-specific accelerators that introduce extra complexity in the deployment. So we expect more developers to specialize in machine learning-based development, at least until this middleware, or for example, the NNN API, becomes more efficient and also more prevalent, let's say. Finally, in terms of cloud-based models, we looked at applications that are using cloud-based machine learning APIs. We found that there are more applications actually using them than including models. we've seen a 2x increase over the last year, and most of them belong to Google AI. And the main takeaway here is that offloading inference, although it has a cost of privacy and monetary cost as well, it is often preferred and most likely because of this fragmented Android ecosystem. So we as researchers need to find automated solutions for optimizing DNN deployment, abstracting all this complexity. So finally, we presented a comprehensive empirical study of the most popular DNN-powered mobile applications. We show that there is a big chasm compared to the state-of-the-art architectures and optimization techniques. And we believe that we are within the first works to paint the landscape and provide guidelines for research, mobile app, and DNN framework developers communities. And without further ado, I welcome your questions. Thank you.